Hey guys, we're doing the last part of this paper, which is paper 2H for chemistry for May 2008. Alright, question 10, which is the final question, gives this reactivity series, and it gives the most reactive to the least reactive metals. And, okay, question 10a says that iron is sometimes coated with zinc to prevent the iron rusting, because iron reacts with oxygen and it basically rusts in air, as you guys should probably know. And the iron does not rust even if the coating of zinc becomes damaged. Now, what is the name given to this method of rust prevention? Now, usually with most metals, which are really reactive with oxygen, they cover them with another metal to prevent the middle metal, the main metal which you want to keep, right? They cover it with another metal so that that metal reacts with oxygen instead of this metal in the middle, and so the metal in the middle doesn't get damaged. So that process is actually called galvanizing. Okay? Galvanizing, and you'll always hear it like galvanized steel, galvanized table, like galvanized spoon or something like that. You always hear that word galvanized. So that's what the process is called. Or it's also called sacrificial protection, because if you think about it, this metal on the outside is making a sacrifice and reacting with the oxygen instead of the metal in the middle. That's another name for it. So galvanizing or sacrificial protection. Or sacrificial protection. Now, question A2 asks you to give one example of where this rust prevention is used. Now, I've already told you galvanized steel. And what is galvanized steel used in? It's used in things such as railings, in cars. Notice how your car doesn't rust, the outside of your car doesn't rust. It's used in, like, for example, the lamps, the lamp posts, they don't rust. It's just used in a lot of different things which use metal. So these are a few examples. Usually what I would do is I'd just memorize two or three, so just memorize these three. And that's it. Question 10A3 asks you how this method of rust prevention works. So this is basically the method of rust prevention. You take the iron, you cover it in zinc. Now, to understand how it works, we need to refer to this reactivity series over here. Now, if we look, zinc is higher on the reactivity series than iron. So that means that zinc will be more reactive to anything in the air, such as oxygen or any other element, because it is higher in the reactivity series. So that means that since zinc, if you were to answer this question, you'd say that since zinc is more reactive than iron, it reacts with oxygen in the air instead of iron reacting with oxygen, and hence rusting is prevented with O2, and hence whatever, just write it, and hence rusting is prevented. So that is the reason, because this is more reactive. So if there's oxygen in the atmosphere, instead of this iron here, which is less reactive, reacting with the oxygen, the zinc will just react with the oxygen, and it'll just keep reacting with the oxygen, and at the end of it there will be a layer of zinc on the top, which prevents any iron in the future in the middle from reacting. Question 10b says that a student is given some solid nickel nitrate pieces and several small pieces of magnesium, zinc, iron, copper, and silver. Now you have to describe and explain how he can find the position of nickel in the reactivity series above. So now we have nickel nitrate, so NiNO3 2. And when nickel is a metal basically, and I'm sure you guys know what displacement reactions are. So when you react a metal salt with a metal, if another metal is more reactive than the original metal, let's say if Mg is more reactive than nickel, Mg will replace nickel and form MgNO3 2 plus Ni. So that's how the process works. So if the metal is introduced into the salt of another metal, and if the metal you add is more reactive, it'll displace the other metal. So in this case we have nickel nitrate. So the process we would use to find its position in the reactivity series would just be to take nickel nitrate, right, and add it to all of the metals. So take a solution of nickel nitrate, right, and then we add each of these metals one by one, right, and then if a reaction occurs, i.e. if a displacement reaction occurs, yeah, that means that metal is more reactive than nickel. And so that is the process. So you take a solution of nickel nitrate, you add each of the metals, and if a displacement reaction occurs, that means the metal is more reactive than nickel. So for example, if bubbling occurs or something like that occurs, and a new metal is produced as a precipitate, that means that metal is more reactive than nickel. So that is basically your answer to this question. Okay, so question 10c says that when nickel nitrate solution is electrolyzed, remember electrolysis, the process you covered in the first question, the product at one electrode is nickel, solid, and the ionic half equation is shown over here. Now they're asking whether nickel is oxidized or reduced in this reaction. Now an easy thing to remember is oil rig. Now what is oil rig? Oil rig basically stands for oxidation is loss, and rig stands for reduction is gain. And this has to do with electrons. Remember, oxidation and reduction has to do with electrons. So oxidation means that the substance or the species loses electrons, whereas reduction means that the substance or species gains electrons. So in this reaction, you have Ni2+, it's gaining 2 electrons to form this solid. So that means that the gain of electrons is rig. So that means that reduction is happening in this case. And the reason for that is because Ni2+ gains 2 electrons. So question 10c2 says that a sample of nickel nitrate solution was electrolyzed using a current of 1.5 amps for 160 seconds. Yeah? And they say that 1 Faraday, which we'll call F, is equal to 96,000 coulombs. And what you have to do is calculate the mass of nickel formed. Alright, so before we start this question, let me just explain what 1 Faraday is. And 1 Faraday is actually equal to 1 mole of electrons. Okay, so what we're going to use here is we're going to use that previous equation we had. So Ni plus 2 electrons gives Ni solid, right? And basically this means that 2 Faradays were used. So we're going to use mole ratios to figure out the number of moles of nickel used, and then we can find out the mass of nickel used. So how do we do all of this? Let's just think. So we have the current, fine, and we have the time of the current. Now, as you probably should know, it's presumed knowledge, current, which I'll label with a C, is equal to charge, which is Q, which is in coulombs, charge is in coulombs, per unit time. Okay, so it means that the charge is equal to, Q is equal to current times time. So that means that it's 1.5 times 160, which means that the charge, or the number of coulombs, will be 240 coulombs. So that means that for this whole time, we've used 240 coulombs in this whole reaction to electrolyze this, to cause this reaction to occur. Yeah? So now we want to know how many Faradays we've used. So we want to know the number of moles of electrons we've used. Because remember, we want the number of moles of this to find the number of moles of this to find the mass of this. So we have 240 coulombs. Now we need to convert it into moles of electrons. And that is basically the Faraday. That's where the Faraday comes in. So we know that 1 Faraday is to 96,000 coulombs. Okay? So again, this is ratios. So how many Faraday, or X Faraday, is to 240 coulombs? So now we can equate these. So 1 over 96,000 1000 equals x over 240. So it means that x, which is the number of Faraday used in this whole process, is equal to 240 divided by 96,000, which will give you an answer of 0.0025 Faraday. So now we know that 0.0025 Faraday was used, or in other words, 0.0025 moles of electrons were used. Now, if 2 moles of electrons give 1 mole of solid nickel, so if 2 moles of electrons give 1 mole of solid nickel, how many moles of nickel does 0.0025 moles of electrons give? So again, same process, 2 over 1 equals 0.0025 over x, and x, which is the number of moles of nickel produced, is equal to 0.0025 divided by 2, which is 0.00125. So that means that that is the amount in moles of nickel produced. So now we finally kind of reached the end. So we have the number of moles of nickel produced, correct? And we don't have the mass of nickel produced, but we want to find it. But we always know the formula of nickel, or the molar mass of nickel, right? So that means that we have the molar mass, we have the number of moles. Now following that equations we've done before, we know that number of moles equals mass over molar mass, and the mass equals number of moles times the molar mass. So in this case it's 0.00125 moles multiplied by the molar mass of nickel, which is just 59 according to the periodic table, and that'll give you a total mass of 0.074 grams. So that is the mass of nickel produced when 1.5 amps of current is passed for 160 seconds. Alright, so question 11a says that ethanol can be dehydrated to form ethene. Now you have to figure out the conditions required for this reaction. Now conditions are something you have to memorize, and for dehydration what you need is high temperature, so high temperature, and also you need aluminium oxide. So those are the two conditions. Or you can say hot concentrated phosphoric acid. Like again, refer to the mark scheme because this is nothing I can teach you, it's just memorization. Okay, so question 11a2 asks you to complete and label the energy profile for this reaction. So in the beginning you have C2H5OH at a certain energy level, at certain amount of energy, and you have to just figure out how the products are compared to C2H5OH. Now they've told you delta H for the reaction is plus 35. Now when there's a plus sign, that means that the reaction is endothermic, which means that energy is absorbed while the forward reaction occurs. Now remember, this delta H refers always to the forward reaction. So that means that energy is absorbed. So that means that the products, if energy is absorbed, should have higher energy and should exist at higher energy levels. So that means that C2H4 plus H2O should be at a higher energy compared to C2H5OH, because this reaction is endothermic. Now question 11a3 is asking you to state with a reason the effect of increasing the temperature on the equilibrium yield of C2H4. Now first of all, we know that the forward reaction is endothermic, meaning it absorbs energy, meaning it likes to absorb energy. So if the temperature is increased, there is more energy, more heat to be absorbed by the forward endothermic reaction, correct? So that means that if I increase temperature, the yield of C2H4, so the yield of C2H4 will increase. And the reason for this is the forward reaction is endothermic. The forward reaction is endothermic, and so that means that it'll absorb the increased temperature. So it'll absorb the increased temperature. Because remember, equilibrium always tries to maintain a constant, right? So if it's constant and then the temperature is increased, it wants to remain constant, so it wants to reduce that increased temperature. So to reduce that increased temperature, these substances are going to have to absorb the energy, the extra energy, and so the only way they're going to absorb that extra energy is by going in the forward direction, in the direction of the endothermic reaction. But all you need to really do is say that the yield is increased because the forward reaction is endothermic and it absorbs the increased temperature. So question 11b says that ethene forms an addition polymer, polyethene. Draw the structure of it, showing at least 4 carbon atoms in your structure. So first of all, let's draw the ethene structure. Ethene is eth, meaning 2 carbons, and ene, so it's an alkene, so it has a double bond. Now what happens when polymerization occurs is that one of this bond breaks, right? And then it forms, so you have 2 extra available areas to bond. And then this just happens with a lot of different ethene molecules. So they can just keep bonding to each other basically forever and ever, and they form a big long chain. So now this is the repeating unit. This is what we call the repeating unit of ethene. Now the structure of polyethene would just be, you have to draw 4 carbon atoms in your structure, so you just do 1, 2, H, 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 right? And now there'll be 1 bond, and then it'll bond to another ethene, which had a broken thing. And then that'll have another bond. Now, that's the structure. So, and this unit basically repeats forever and ever. So to show that forever repetition, you just put N over here. You put a bracket around it, and you write N. And just make sure that you draw all 4 carbon atoms. I've drawn them all here. And that's it. Okay, so question 11c says that an organic compound has, okay, so I'll just organize this first. I'll say carbon, hydrogen, and oxygen, and it is 38.7%, 9.7%, and 51.6% by mass. And the relative formula mass is 62, as said here. You have to calculate the empirical and the molecular formula of the compound. Now, the simplest way when you have percentages to find the empirical formula is to divide each of the percentages by the molar mass or the atomic mass of each atom. So in this case, we would divide carbon, we divide the percentage by 12. For hydrogen, we divide it by 1. And for oxygen, we divide it by 16. And that would give you 3.225 is to hydrogen, which is 9.7, is to oxygen, which is 3.225. Now, in essence, what you've kind of done right here is you've converted them all to like moles, okay? You've converted them all to moles because you've assumed that these percentages are like their masses out of 100. So if you had a mass of 100 of a compound with carbon, hydrogen, and oxygen, if you had their mass as 100 grams, that means 38.7 grams of carbon is in the thing, 9.7 grams of hydrogen is in the thing, and 51.6 grams of oxygen is present. So what you've done is you just divided by the molar mass, because you know number of moles equals mass over molar mass, and you've converted them into moles technically. Okay, and now they're all in moles. So this is their ratio of in moles to each other in the substance. Because remember, when you have any, like for example, if you have Na2O, right, that means that there are 2 moles of Na to 1 mole of oxygen. So the same way, 3.225 moles of carbon to 9.7 moles of hydrogen to 3.225 moles of oxygen. Now all you have to do is simplify this ratio and make it into the whole number form, so 1:2:1 or something like that. You make it into that whole number form and that'll give you your empirical formula. So in this case, what I usually do is I divide by the smallest number. So in this case it's 3.225. So you divide everything by 3.225. Again, 3.225, you divide it by 3.225, and you'll get 1 is to 3.0077 whatever is to 1. Now this is approximately 3. So you just assume that it's 1:3:1. That means that this is the ratio of carbon to hydrogen to oxygen in the substance. Okay, so that's the simplest ratio, and this is called the empirical formula. So that means if we were to write this, it's carbon H3O, and that is the empirical formula. Okay, so now we have the empirical formula. Fine, that's correct. Now what we need is the molecular formula. Now how do we get that? Okay, so we have the empirical formula, and we have the relative formula mass of the compound as 62. So now there's this simple thing you can do to find the molecular formula. And remember, the empirical formula is the simplest ratio, while the molecular formula is the actual ratio. So what we do is we take the relative formula mass, and which is 62 in this case, and we divide it by the empirical formula mass. Now the empirical formula mass is just the molar mass of the empirical formula. So in this case it's just 12 plus 3 times 1 plus 16, and that is about 28 plus 3, which is 31. Okay, so you take the relative formula mass, you divide it by the empirical formula mass, in this case it's 31, and you'll get a number, which in this case is 2, because 62 divided by 31 is 2. Now what you do with this number, right, what do you do with it? What you do is you multiply each of these numbers, in this case, by this number, and that'll give you your formula mass. So instead of C1 H3O1, it should be C1 times 2 H3 times 2 O1 times 2. And what you'll get is C2 H6O2. And this is basically the molecular formula of the compound. So the empirical formula is CH3O, while the molecular formula is C2H6O2. And the way we found the molecular formula is to divide the molecular formula mass by the empirical formula mass. And then we get a number. We multiply each number in the empirical formula by this number. So that's it. Alright, so we're finally done with this really long paper. Please comment if you have any questions. I might not have explained some things well. Again, first video after a long time. Please rate this video, again 5 stars please, and subscribe to the channel as well. Thanks a lot for watching, and I will see you on the next video.